Leo's lived in Essex for most of his life. He went to Colchester Royal Grammar School, I believe, and he went on to study physics at University College in London. I hear that he spent a year down a mine in the USA operating equipment chasing neutrinos, and he spent 2 years at CERN trying to create a black hole. So he knows quite a lot about what we're going to be talking about tonight. He's a regular attender at Imaging Wednesdays for the NEAS and Club Night, and goes by the name of Astro Ninja, which is why you can see that's what his picture is. He's been kind enough to introduce us tonight to the new physics particle. So with that, Leo, please take it away.
So there's been some new results in physics recently. You've probably seen about it on the news. I just thought perhaps I'd take the opportunity to sort of tell you a bit about it if you're interested. So, what's happened then? So, what have I got to say about this? What's happened? Who knows? This is too slow. What does it mean? Does it mean anything? I don't know. And how important is it? Well, I'll try and answer some of these questions, one way or another. So, I've just noticed that the this thing over here is in the way of my slide, and I can't. Okay, well, anyway, I'll carry on. Hopefully, it won't matter. Right. So, two major experiments have simultaneously published new results with very interesting data. So, I'm going to tell you about what these results are, what it means for particle physics, and what, if any, implications there are for cosmology and astronomy. So, to give an overview of what I'm going to talk about tonight, I'm going to talk about muons and the Standard Model, the LHCb experiment and the G-2 experiment, which you may well have heard about in the news, the results of those experiments and the significance of those results, and the impact on particle physics and the importance for astrophysics, if there is any. So the experiments in question, here's a nice big world map for you. So one of them is here in Switzerland and France, and the other is here in Chicago in the United States of America. And that one is called Fermilab, which you may well have heard of, and this one is called CERN, and I certainly hope you have heard of that, otherwise I'll be very disappointed. While we've got this nice big map, I just thought I'd mention that in America, they have this scrawny, dried out stuff that they call bacon. I don't know why that's had to happen to us, but anyway, it has. If you want proper bacon, you have to ask for either Irish bacon or Canadian bacon is nearly as good, but it's not the same thing. And in France and in parts of Europe, they have this sort of diced up stuff which they call lardon, and that's not much better, to be honest. But anyway, that's neither here nor there, really. So let's get on to talking about the experiments. So this is a aerial view of Fermilab. It's a very big site. There's actually a buffalo ranch on the site because it's that big, which is kind of cute. If you look towards the middle and just over to the left, you can see a little sort of perhaps A-shaped building. I'll zoom into that in a bit, but this is the overall site. It's a very large site. It's on the outskirts of Chicago. And CERN, this is the ring. It's all underground, and mostly underground. It's mostly in Switzerland, but there's also quite a lot of it in France. In the background, you can see the mountains there, and you can see Lake Geneva. It's 30 odd kilometers round underneath the ground. The Fermilab, they have a ring as well. You can see the two rings there actually. They're about 8 kilometers, I think. So if we zoom in a bit, this is Fermilab, the actual. This is called the high rise, the building. It's quite an iconic building, where most of the physicists are kind of and accelerator physicists, and everybody hangs out in there and does this stuff. This is a close up of the site of CERN. It's not quite as exciting looking, really, but although there's some nice mountains in the background again. And if I want to zoom in even further, this is the experiment G-2, which is a nice ring, and there's a little logo there. And this is the LHCb experiment um, at um, at the LHC, which is a detector within the LHC ring. So these are the two experiments that I'm going to be talking about tonight. So let's start. Oh, whoops. Right. So G-2, as I said, is a Fermilab in Chicago, USA. There's around about 150 people from 40 different institutions from 7 different countries working on that experiment, and it studies spinning muons. I'm going to get onto that in greater detail in a bit. The other experiment is LHCb, as I said, which is at CERN, which is in Switzerland and France. That has 1,260 people from some number which I can't see because the things are over it. Is it 74? I can't see. 74 institutes in 16 countries. And that experiment has noticed a deficiency of muons, and that's what it's reporting. Now, the thing I want to say is that even though both of these experiments appear to have something to do with muons, the actual scientific program, if you like, of the experiments are unrelated. They're not really anything to do with each other. They just happen to have muons as part of what they're doing. So, but anyway, I'll get onto that. In any case, the next thing I'm going to do is talk about muons. So muons are indivisible particles. That means that they're one of the fundamental building blocks of the universe. They're very similar to electrons. They have an identical charge to the electron. But one of the peculiarities is that they are about 206.77 times heavier than an electron. So that you could imagine that they're like an electron's big brother. Muons also have a lifetime of 2.2 microseconds, which means that they only exist for 2 millionths of a second before they decay into electrons and other things, which might not sound like very long, but in particle physics terms, that is quite a long time. And with our modern electronics that we have, 2.2 microseconds is plenty of time actually to study these particles, which is very nice. So what am I going to talk about next? Right. So cosmic rays is where we first discovered muons. So high energy particles from space, from the sun and places like that, impact on the Earth's atmosphere and cause this big shower of particles which comes down to the Earth. And we started studying these particles. And in there we found muons. That was the first time we found muons, and also antimatter. So these cosmic ray particles are a bit like kind of space invaders that kind of invade us from space. So we can study these cosmic rays on Earth in something called a cloud chamber, where we can see their tracks as they pass through the device. And in this case, we can see this tightly curled particle on the bottom with a blue track is an electron. The longer tracks that go across the page are muons. Now, the magnetic field that is in this cloud chamber shows that there are some that curl clockwise and some that curl anti-clockwise. So the blue one that's curling clockwise is an electron, and the red one that is curling anti-clockwise is the antimatter particle equivalent of an electron, which is called a positron. So cosmic rays and cloud chambers have been able to um, show us that not only that there are these muons, which are curved by a magnetic field, but curved much less than an electron because they are heavier, but also has showed us antimatter as well. So all of these particles, in fact, everything um, that we know about is encapsulated in this handy little diagram that we call the standard model. It's a bit like the periodic table of chemistry, but this is for physics. Um, so what's interesting is that if you look at the left-hand column, I've got up, down, electron, and neutrino. Um, up quarks and down quarks um, make up protons and neutrons, and together with electrons, that makes up practically all of the matter in the universe. And together with neutrinos at the bottom, which are kind of like ghosts of electrons. They're strange particles that a bit like ghosts in Pac-Man. That kind of, I don't know. But anyway, basically the important thing is that the left-hand column more or less encapsulates all of the matter that we see around us. So if we go to the second column and the third column, this is what we call exotic matter. Now you'll notice that they're all kind of grouped together because they're all relative to each other, and you'll see next to the electron is the muon, which I said is the rather heavy brother of the electron. They all seem to be kind of related in a way. So next to the up and down quark is the strange and the charm quark, and next to that is the top and bottom quark. I'm told that the top quark is actually 27 years old today, believe it or not. It wasn't discovered for so long because it's quite considerably heavier than the rest of the particles, which is something that we don't yet understand. But anyway, top and bottom are sometimes called truth and beauty, but that's old school. I'm going to call them top and bottom. And on the right-hand side, we have these particles which are known as bosons. And these are responsible for the 4 known forces of nature. So we have the gluon, which is responsible for the strong nuclear force, which holds particles together in the nucleus. The photon, which is responsible for all electromagnetism, light, everything we see, electric effects, magnetic effects, light, they're all done by the photon. The 2 at the bottom, the W and the Z, are to do with the weak force, which is related to radioactivity. And then over to the right, we have the graviton, which is another force of nature, but does not fit into this neat puzzle that well, unfortunately. And finally, there's the Higgs, which has just been recently discovered and is responsible for giving mass to all of these particles. The theory would be a lot simpler if everything was massless like the photon. But obviously, that's not the way it is. These particles, for whatever reason, have mass, and the Higgs we have discovered is responsible for that. So this is a nice, neat little picture. It's not quite as simple as this. To start with, I've said that there are antimatter particles as well. So for each of these particles that we see, not quite all of them, because the photon, for example, doesn't have a charge, so it's its own antiparticle. There's no anti-photon. It is its own anti-photon. But all of the other particles, or most of the other particles, have an antiparticle associated with them. The other additional complication is that the 6 at the top, the up, down, the charm, the strange, the top, and the bottom, actually come in 3 types, which we call flavors: red, green, and blue. So there's not 6 of those, there's actually 18 of those. And so in total, there are 61 particles, which seems like a lot, but they've all been seen, they've all been measured, They've all been discovered. There's nothing airy fairy about any of this. Every single one of these particles has been discovered, found, measured completely. Although the only strange thing is that we only really need four of them right at the beginning to to cover most of the universe. But anyway, so what's the next thing? Right, so I'm going to get on to LHCb now. So LHCb is one of the four major experiments at CERN, along with CMS, ATLAS, and ALICE. And the Large Hadron Collider is an experiment which smashes protons together to make new particles. Now, LHCb is looking for something called CP violation, which is not quite the same kind of thing as what the Atlas and CMS were looking for, which is the Higgs, which they've now found. LHCb is studying reversible processes, which is hoped might be able to partly explain the matter antimatter discrepancy of the universe. So the idea is that if you have a process which is capable of going backwards and forwards, if you do it many, many times, you want to make sure that you end up with the same amount that you started off with as that you that you were transforming them into, and it turns out that's not the case. Over time, there's an asymmetry, which is very interesting, which might explain why there doesn't appear to be any antimatter, but there's lots and lots of matter. Let me just take a sip of water. Hang on a sec. Right. So this is a sort of animation of what the LHC does. You'll see anti-protons and protons get spun around the ring, and then they're collided together and they make this big explosion. So if you look down on the left bottom hand side, you'll see this is the CMS detector. This is a kind of cross section through the CMS detector. But what you'll notice is that it is designed to completely surround the point where the collision occurs, because when you're looking for a Higgs, what you want to do is measure absolutely everything that comes out of that explosion so that you can piece it all back together again and work out what happened. LHCb is a different kettle of fish because it is asymmetric, and that is because they're looking for certain types of particles, which it just so happens, I just wonder where I've got my mouse. Oh, look, it just so happens that they tend to stay close to the entry and exit point. They tend to almost kind of go through each other. Whereas in a CMS detector, things will go up and down and left and right quite a bit. The particles that they're looking for in LHCb will just go along this axis predominantly, which is quite handy because it means that you don't need to spend all this money on all this extra detector over here. You can make a much smaller detector, and you can use that money to make it a much finer kind of granularity, which is exactly what they want for this type of experiment. So what they're looking at specifically in LHCb, the B stands for bottom, by the way, it's Large Hadron Collider bottom experiment. And they're looking at these things called B mesons. And B mesons are a type of particle that is produced during one of these collisions. They're not interested in the entire collision, they're just interested in the B mesons that are produced as part of that collision. So a B meson is made from an anti-bottom and a down quark, and you can see using my little periodic table, I can show you exactly what the constituent parts of that are. I should say it's a red. The red circle means it's an anti-bottom. It's not a bottom, and the blue one means that it is a down particle, which is a matter down particle. Now, this B meson, once it's produced, will also decay further into two possibilities. It can either decay to a K plus, which is a strange particle, and an up particle, together with an electron and a positron, so that is a particle antiparticle pair. Or it can decay into a kaon again, but this time with a muon and an antimuon. So, what's interesting about this is um, our current knowledge of particle physics. There is no preference for whether the electrons should be produced or whether the muons should be produced. You'll notice, I'll just point out that going the next step to the right, there is the tau particle. So you might ask, is it possible for the tau particle and an anti-tau to be produced? But there's not enough energy in this collision to make taus. They're very heavy. So you can only make electrons and muons. In any case, LHCb reports an excess of electrons being produced over muons at 3.1 sigma. So what on earth does that mean? Let me tell you. Excuse me. Right. So sigma is called the significance, and it's quite an important part of this whole business. So let's imagine that a little alien came down and visited us and wanted to see what we were up to. And the first thing that came to our mind was to show it a coin. I don't know why the first thing you'd show an alien is a coin, but anyway. So you flip the coin and it lands heads, let's say. And the alien says, "Oh, right, you've got a coin." And when you flip it, it comes up a head. And it takes the coin and it flips it and it comes up a head again. And it says, "Oh, right, so you've got this thing which has got a head on it." But then you take the coin back from the alien and you flip it again and it comes up tails. And the alien says, "Where did that come from?" And you have to explain to the alien that there's a head and a tail. So then you flip it again and you get another head, let's say. And it says to you, "Well, is there anything else that could happen?" And you say, "Well, no, there's only one head and one tail, that's it." Um, but the alien's not convinced. It wants to flip the coin a few more times to see if anything else happens. So the question then becomes, how many times do you need to flip the coin before you've convinced yourself that heads and tails is really all that you can get? Let's try giving it a dice, and it rolls a dice and it gets a 2, and it rolls it again and it gets a 3, and it says, "All right, well, this thing has got 2s and 3s." You could easily roll a dice 10 times and maybe never get a 5. But if you rolled a dice 100 times and never got a 5, then you'd probably start to think that was a bit strange. But again, the question that I'm asking is, how many times do you feel that you need to roll the dice before you can convince yourself that you know how many sides there are and what's on the dice? Let's make the situation slightly more complicated. Let's say we've got a 6-sided dice, but there are 4 ones and a 5 and a 6. That would be even more complicated to establish how many of each of the different numbers were on each side. So how many times would you decide that you felt you needed to roll that particular die before you decided you knew what was on each side? And this is what significance is all about. So 3.1 sigma means that, if you like, they've rolled a dice 1,000 times and they're pretty sure that they know, or a coin, let's say, that there's only a head or a tail, and that's it. 4.2 would be more significant, that's a bit like rolling the dice 40,000 times to really make sure that you really understand what's on the heads and the tails or the spots on the dice. Um, but for these days, for most scientific experiments to feel as if they're valid and they've made a scientific discovery, they will want something called 5 sigma, which means that they've rolled the dice 3,500,000 times. So they're absolutely convinced that what they think they're saying is the truth. So physicists are very patient people, and like this frog, they have to wait until the time is right for the right moment to make a discovery. If you if you if you make too much of a song and dance with a 3.1 sigma discovery, you run the risk of making a fool out of yourself later down the line if somebody else or even yourself later prove that it was just a 1 in 1,000 chance and it was just a random fluke. So I'm going to take a pit stop at this point and ask anybody if they've got any questions so far. So far I've been talking about muons and the standard model, the LHC and LHCb experiment, and the significance. So, any questions? I'll have a little bit of water so far. Right, well, if there aren't any questions, I'll press on, I think. Shall I press on? Righto. So, the next part of the talk is G minus 2. So, G minus 2 is this lovely ring experiment at Fermilab. And the way this works is as follows. So G minus 2 studies the behavior of muons, but it's doing something quite different to LHCb. So muons spin on their axis, as all particles do, a bit like the Earth spinning on its axis. And they're charged particles. They've got the same charge as the electron. So as they move, they generate their own little magnetic field. If you then put a muon inside an external magnetic field, you expect it to spin, but it will also precess, a bit like a gyroscope. So you can see in this little animation that the gyroscope obviously is spinning, but it's also doing this little wobble, which is the precession. And that is because, in the case of a muon, this is because it has its own magnetic field, but it's also, in the case of this experiment, within another magnetic field, which causes this precession. So G minus 2 uses the existing accelerator facility at Fermilab to produce an intense beam of muons. And these muons are store-bought muons, which means that the properties, the energy, and the various properties are well understood. Not random particles from space like cosmic rays, which would be very difficult to manipulate and study, and there wouldn't be enough of them, so it would be very difficult. So they use this beam of muons that they make at Fermilab, and they put them in this ring, and the muons circulate around the ring about 400 times before they decay, and they're able to study them whilst they're in the ring. Now, the amount that the muon wobbles around is a precisely known quantity. That amount that it kind of moves from left to right, from kind of dead center, if you like, that is a precisely known quantity. Um, in quantum mechanical terms, it's simply 2, the number 2. So G minus 2, as you might be able to imagine, is the anomaly. It's the deviation from the expected value of 2. In fact, we already know that it's not quite 2. There are these things called quantum corrections, but they're also fairly well understood. And so this experiment um, is looking for quantum corrections that we don't know about yet, which will cause a deviation um, from this of the wobble. Now, if you're feeling a bit confused about what I've just said, I don't blame you. So I'm going to try to draw an analogy to make it a bit more clear. So let's imagine that we've hired a squash court, and in that squash court, I'm going to put 2 kind of like poster boards with wheels on, some sort of board. That I'm just going to put 2 of these on in the middle of the squash court. Then what I'm going to do is I'm going to get 10,000 tennis balls and I'm going to pour them into the squash court. And what's going to happen? The balls are going to bounce around all over the place. Some of the balls are going to hit the poster boards and going to make them move. But with the um, with the boards at this kind of distance, there should probably be, on average, the same amount of balls that hit them from the left as hit them on the right. So overall, they should probably stay in the same place. But now let's imagine, oh, sorry, this is a bit like Pong, I suppose, in a kind of way. But now let's imagine that I put the 2 boards much, much closer together. In fact, so close together that there isn't enough room for a tennis ball to fit in between them. So now if I do the same thing and pour all these balls into the squash court, the poster boards are going to get hit from one side, but they're not going to be hit from in between because there isn't enough room in between for any tennis balls to be there. Okay? So this is actually a known effect in physics. It's called the Casimir effect. And it's caused due to the Heisenberg's uncertainty principle, which says that even a photon of 0 energy, which ought to be nothing, has a possibility of having some energy. And what that amounts to is that there's no such thing as nothing. So everywhere in our universe, there are these quantum fluctuations of particles that are coming into and out of existence, which are like these tennis balls. They appear in pairs, and if you're able to put a metal sheet or some kind of object in space that is sufficiently small that certain particles can't fit in that gap, then they will be pushed together because they're being hit by things from the outside, but there's nothing on the inside to push back out again. And you might think this is very strange, but we do see this in various parts of physics. As I said, this Casimir effect has been measured. There's also this thing called the Lamb shift, which we see in the hydrogen spectrum, where there are 2 energy levels which we expect to be the same, but they're slightly different because of this interference from these particles in space. A proton, it also turns out, is on average 1/6 antimatter at any given time because there are these particles appearing and disappearing out of nowhere. And you may have heard of Hawking radiation, which is the process by which black holes evaporate. And that is also actually as a result of this, where a particle antiparticle pair are produced on the event horizon, and one particle falls into the black hole and the other particle escapes, which over a very long period of time causes the black hole to evaporate. So G-2 reports a measurement of an anomalousness of this G factor of 4.2 sigma, which I said is 1 in 40,000 chance of that being strange. And this is, sorry, not being strange, I should say. And this is attributed to these particles in space buffeting the spinning top, the spinning muon, in ways that we do not yet understand. So, is anybody still awake? Or are you all sleeping beauties out there? I don't know. So, anyway, what does this all mean? Let's try and get to the crux of it. Unfortunately, LHCb and G-2 cannot say anything definitive yet. LHCb is only 3.1 sigma, and G-2 is 4.2, which is better. But neither of them are in a good enough state at this time to say they've made a discovery. But moreover, neither of them are in a particularly good state to explain what it is that they're seeing. So it's fair to say that both are seeing something unexpected, which is a strong indication of new physics, which is very good, but they don't know what that is. In any case, new physics could be a major event. The general interpretation of both of these experiments, although it's not necessarily the same interpretation for both experiments, I should say, it could be two different causes. In fact, it's quite likely to be two different causes. But it's significant because the proposed solution is that either it's a new particle of nature or a new force of nature, or both, perhaps. A photon, for example, is a particle, but it exhibits the electromagnetic force. So the photon, in a way, is both a force and a particle. So this could be the case of what we're seeing here. So what? So are you all holding on to your seats? Because a new particle could be dark matter, and a new force could be dark energy, in which case we might have cracked both of the most difficult problems in cosmology at the same time. It's a possibility. But as it turns out, the theorists have had some candidates for dark matter for quite some time, but there's a rather unfortunate bitter taste to it, because you need to do this. So, as I said before, there are 61 particles that we know of, and we have these two particles here, which are very promising candidates for dark matter. But unfortunately, it means that you need to invent another 61 particles, of which we've seen none, in order to facilitate this. So it's a bit of a double-edged sword. So, you know, your kind of solution is worse than the cure is worse than the disease in a way, because you've had to create this enormous amount of additional particles in order to accommodate your dark matter particles, none of which we've seen yet. So that is a glaring kind of omission in what would be the new standard model if it turned out that this was the case. Dark energy also is sadly not the first choice of the theorists um, as an explanation of what this fifth force might be. Um, Cosmologists would like to imagine that the fifth force is something called a cosmological constant, which is a kind of energy field. It's the right sort of thing. Um, and there's a dynamical form of this called quintessence. But these theories operate at astronomical scales. And obviously, we're talking about particle physics experiments, which are operating on subatomic scales. And these things don't really gel together very well. Um, although this EBOS experiment that the Chinese have done has just detected dark energy with a massive 11 sigma significance. Um, so it seems very unlikely that dark energy is just imaginary, which is good, I suppose. But really, nobody in the world is getting much closer to establishing exactly what it is, unfortunately. So, final political words. So, what was I going to say? Right. So Fermilab is America's flagship laboratory. And when the Tevatron shut down, so the Tevatron is like their little mini LHC, it shut down in 2011, which immediately caused a bit of a problem because you've got all these physicists that are sitting around wondering what to do. And um, there wasn't very much to do. The CERN had just discovered the Higgs, so that had kind of messed up their plans a bit. Um, and CERN also made the gratuitous error of actually finding the Higgs, which meant that they didn't really have very much to do once they'd basically completed their mission. And so both of these labs, CERN and Fermilab, found themselves in a slight quandary that there were certain elements of their governments and their kind of sponsors and things that were starting to ask questions like, well, what is the point of you being existing anymore because you've both done what you said you were going to do? So from that point of view, these recent results that have come from Fermilab with the G-2 experiment and CERN with the LHC B experiment, it's quite fair to say that they saved their bacon quite a bit, really, or their lardons in the case of the of CERN. So, in conclusion, we've had two big new results from two major labs. There is tantalizing hints of new physics. It's very exciting for particle physicists, but there aren't really any answers. So we're just going to have to carry on looking, really, I think, and see what we find behind the sofa. So that is it. Thank you very much. And um, do you have any questions?
That was fantastic. Thanks, Leo. I've got a question. You said that both of the experiments are not yet at the right significance. So how many times are they going to have to repeat these experiments, and over what time frame are we going to be able to get to 10 sigma in either of them?
Well, probably five sigma will be good enough. G-2 will is expected to get to that kind of significance in a couple of years. But in the meantime, they've got things that they can do. They can try and improve the accuracy of the equipment and the kind of the ways that they study the data and stuff like that, which can help to improve the significance. LHCb, I'm not sure if they are going to push that very much. The thing is that the LHC is having an upgrade. I believe it's shut down at the moment. So when the LHC reopens in a couple of years' time, they will restart the experiment and they'll they'll be able to take a kind of running, or is it hit the ground running or whatever, and probably be able to supersede the results they've already got in another year or so. So in both cases, we're talking about a couple of years probably. So it's just to whet everybody's appetite in the meantime.
And just one more. And so even if they do get to the point where they can say they've made a discovery, there is an extra force or an extra particle.
Yeah.
They're not really in a position to say what that might be.
Absolutely. Yeah. Unfortunately, not.
They're just basically posing more questions, really.
Yes, that's pretty much the case. So I suppose what we're kind of hoping for is that it's perhaps spurs on other experiments to take place, which might be kind of look at the same problem from different directions. And when people start kind of combining their data, then you can start to you get more, you get a bigger bang for your buck if you're looking at it from multiple directions. Especially from the theorist point of view, they can start to kind of guide people and guide experiments into what sort of direction it might be more a good idea to look in to get better results. In the meantime, cosmology might be able to kind of feed into it as well. So it's all sort of small steps, but hopefully heading in the same direction overall. So, any other questions at all?
Thanks, Leo. Really fascinating talk. I didn't quite understand your comment around the additional 61 particles. You mentioned about the dark matter and the dark energy, and then all of a sudden they're needing to be these other particles. Do you mind explaining that a little bit more?
Yes, absolutely. So, so there is a theory out there, and it's called supersymmetry, and it's been around for quite some time. And supersymmetry requires these extra. It's like a mirror image of the particles that we already have. Although it's the mirror's a bit like one of those funny mirrors you get at the circus, where your head's really small and your tummy's really big, or some sort of mirror that Alice looks through in Wonderland. But anyway, by duplicating all the particles that you've already got, it lends itself quite nicely to a theoretical kind of a simple theoretical extension of what we already have. And also it fits in quite nicely with things like string theory, which you may have heard of. It's the most kind of simple logical explanation, and it just so happens that it also provides a convenient kind of location for these dark matter particles to be in, which would explain quite nicely why we haven't seen them before, but without kind of going completely kind of white rabbit and making up something completely and utterly different. So supersymmetry, although it might seem a bit kind of heavy-handed, by adding these extra 61 particles, is actually one of the simplest extensions to the theory that we've already got, which will also, as it happens, potentially accommodate dark matter. Does that make sense? Have you got?
Yeah, thanks. Yeah.
So, does anybody else have any questions? Any more questions?
Yes, me.
Yeah.
What are the implications for cosmology? You say about dark matter and dark energy, but you've described a lot of new physics, but you haven't touched much upon cosmology.
Yeah, well, at the moment, I think we're fairly confident that dark matter is definitely there, but Nobody knows what it is, and it's very peculiar that it appears to interact with gravity, but doesn't interact with light. And actually, these peculiar heavy particles that are introduced by these extra 61 particles that I talked about actually fit in. That is described by them quite well. They fit the criteria of dark matter quite well. So we're potentially looking at an explanation of what dark matter is, which is something that I think a lot of people are quite eager to find out about. And as I also said, it could potentially be dark energy, which is an even bigger question, but that is even vaguer, I'm afraid. And whether anything will come with that, I don't know. But it's just a tantalizing possibility that these things might kind of neatly tie up, but we're quite a way away from that at the moment, unfortunately.
Okay, thank you. So dark matter and dark energy are just hypotheses, and you think that by actually discovering some meaningful particle, they'll nail it down that way.
Well, that's definitely what the particle physicists would like to do, and presumably the astronomers and the astrologers would kind of like to know what dark matter is, ideally. So yeah.
Okay.
Any further questions at all?
Yeah, what's the big tie-in with 80s games?
Ah, how many games did you see? How many games did you see? So
5, I think.
not just computer games, but all sorts of games.
Maybe 6. Yeah, the Alice in Wonderland board game.
Yeah.
You had Frogger,
Yeah. Any?
Pac-Man.
Pac-Man, Space Invaders.
The one crossing the road. What was that? Was
Yeah.
that?
Yeah, that's Frogger.
Well, I
Pong?
think I've dubiously got 8. So there was a
I
squash
see
court.
Pong. Yeah.
I got a squash court, so I've counted squash. There was the table tennis on the 50p piece, and I don't know, you can play a game with dice, I suppose. And we've got Space Invaders, Pac-Man, Pong, this pit stop game, Frogger, and Sleeping Beauty game there. So 9, I think, depending. Okay. Well,
Fantastic. I think we should all unmute and give Leo a round of applause if we can do that.
very much.